Hi, Pre-Calc. This is Unit 9, Day 31. At least I think it is, if I've counted correctly. We are really coming to a close very soon here with our trig applications. We got a couple new lessons left, one of them being on area and arc length. And this might start to sound a little bit familiar from geometry because you talk about the area of just a sector of a circle in geometry. So it's the area bound by this arc, and then it's cut off by these radii. So we have some central angle theta there. And the way we're going to derive the formula is I am specifically going to derive this in radians. So in geometry, you probably looked at it more often in degrees than in radians. But in radians, I'm going to compare the area of that section that I've labeled A to the entire area of the circle, pi r squared. And what that would then result in is if I compare the central angle theta here to the entire number of radians in a circle, which is 2 pi, we can use this proportion right here to solve for A, which is that shaded area. And that's going to give me the formula that we'll use for area of a sector. So if I cross multiply here, 2 pi times A would equal pi r squared times theta. And in the last step, if you divide by 2 pi, divide by 2 pi, divide by 2 pi, we're going to wind up getting that the area equals, well, the pi's will cancel out. So essentially it becomes r squared theta over 2, which commonly is written as a 1/2 out front. Instead of dividing that by 2, I'm just going to write 1/2 r squared theta. And that is the formula I'm going to use every time I go to find the area of a sector. But like I've mentioned, the way we've developed this is I'm comparing theta to 2 pi. So when you plug in a theta right here, it has to be in radians. A lot of you might forget that. I shouldn't say a lot of you. Some of you might forget that. So make sure you make a big deal of that in the notes. If you're given a central angle in degrees, we got to convert it. Okay, let's try this very first example here. So for number 1, we have that we're going to find the area of a sector for the diameter of 12 centimeters. And it's intercepted by a central angle of pi over 3. By the way, you don't have to redraw this picture every time, but just to give you a little bit of an idea, you should have a good instinct as to what pi over 3 looks like. I mean, pi over 2 is 90, so pi over 3 it's a 60-degree central angle. It might look something like this. So here's pi over 3. And we know that the diameter is 12, so I'm actually going to jump right away to saying that the radius is 6. And I want to find, what's the area of this shaded section right here? So if I use my area formula, 1/2 r squared theta, the radius is 6. Theta is pi over 3. And because that's in radians, I get to plug it in as is right away, which is half of 36 times pi over 3. Let's see, 3 goes into 36 12 times, and 2 goes in there 6 times. I think if I've simplified that all correctly here, we wind up getting 6 pi. Now, I don't really care too much about how you label units. If you're going to label them, I want you to label them correctly, though. This is square centimeters, okay? Because we're talking about an area. So 6 pi square centimeters would be the exact answer. If I said round, we could, of course, do that. Find the area of a sector intercepted by a central angle of 75 degrees, whose radius has a measure of 7 inches. So I'm not going to redraw the picture. We can kind of imagine what this would look like. Radius is 7, 75, again, just short of 90 there. But the biggest difference is when I go to use 1/2 r squared theta, I know that theta must be in radians. So we're going to quickly off to the side convert to radians by multiplying by pi over 180. Now, it's up to you if you want to reduce that or not. Certainly you can type that into the calculator, 75 divided by 180, and hit math frac. So that would reduce to 5 pi over 12. All right, so then if I go from here and say the area is 1/2 of r squared, so that's 7 squared, and then times 5 pi over 12. To simplify, I'm going to leave this in terms of pi again, so just be careful here that we don't make any mistakes in terms of the way we're going to type this in. All right, what would be on top with pi? It would be 7 squared times 5, so 49 times 5 up top is 245, goes with the pi. And the bottom is 2 times 12. I can do that without a calculator. That's 24. And then this, again, would be inches this time, squared. Okay. We'll skip the next one for now. Hopefully you get the idea that area of a sector, and we'll extend this concept by the end of the lesson. Area of a sector is 1/2 the radius squared, and then times that central angle, but in radians. We're going to do the same thing right now with arc length. Okay, so we're not shading in the section. Arc length is what is the length of this piece on the outside. Okay, so it's a part of the circumference. So in order to find the length of that piece, we are going to need to know the measure of the central angle theta. And I'm going to compare the length of this piece to the length of the entire outside of the circle. Circumference in terms of the radius is 2 pi r. I know it's also pi d, but I typically write my formula with 2 pi r. You'll see why in a second, by the way. So from there, we've got theta over 2 pi over here. We're going to compare the central angle to the total number of radians in a circle. Go ahead and cross multiply just like we did when we did area of a sector. So the length times 2 pi equals 2 pi r times theta. And in that last step, divide the 2 pi over to get that the length equals, look how nice the cancellation happens this time. 2 pi and 2 pi go away. So the length is equal to r times theta, where theta must be in radians again, okay? So the only reason I'm making a big deal about this is a lot of what we've done in this unit so far, think about law of sines, think about law of cosines, ambiguous case. That has been a lot of degrees making its way back into our course. Well, if I'm using these formulas, I have to plug in an angle in radians. Let's do the question that we did earlier, but now we're gonna think of the arc length. So I wanna find the length of an arc if the diameter is 12 and the central angle is pi over 3. You know, don't expect me to draw a picture for every one of these, but just to show you what I'm looking for, this length L spans from here to here, whose central angle is pi over 3. And again, if diameter is 12, that means radius is 6. So very simply, L equals the radius times theta. The radius is 6. Theta is in radians already, so I get to plug in pi over 3. And we get the length is 2 pi. Now, if we want to be careful about units here, we're talking about linear units, no more square units of area. So the length would just be 2 pi centimeters for this piece of the circle. All right, it won't be too much of a surprise when I go on to number 2 here. And now I'm going to give you a central angle in degrees. Okay, so we know the radius is 18 inches and the central angle is 20. So really quickly, maybe off to the side, convert that into radians. And let's see, this would reduce to pi over 9. So that has a decent value to reduce there. The length, therefore, is the radius of 18 times the central angle pi over 9. And if you can convert between degrees and radians pretty quickly, these questions really are not too challenging. 9 goes into 18 twice. So coincidentally, this one winds up being 2 pi as well in terms of the arc length. Okay, so we have an 18-inch radius with that central angle. That little part on the outside of the circle, if the central angle is 20 degrees, would be approximately 2 pi inches. 2 pi we know is about 6.28. So if you want to think of the decimal approximation to give yourself some context, you can do that. The application of arc length that I kind of like thinking about is the distance between two cities. And we'll do this one today and we'll save this one for class tomorrow. So we're going to look at the distance from Charleston, South Carolina, which we're given the degrees latitude here, and Toronto, Ontario, Canada, which is at 43 degrees north latitude. Now, when we do this type of application, what we're thinking about, we think about the Earth being round and spherical here. The cities that we're given are going to be approximately on the same line of longitude. If they're on different lines of longitude, it requires additional calculations, but we won't see that in our course, okay? What I want you to think about is, where the equator is. The equator is at 0 degrees north. So we know that Charleston is at 33 degrees north. So 33 degrees north of the equator might look something like this. And I'm going to label this as South Carolina. And therefore 43 degrees north might look something like that. And there's Toronto. So I want to find what is the distance from one city to the next. Well, that distance, this length right here, is the length on a curved surface. Because again, the Earth is round. So where it's not a linear distance, we're not going to dig a hole through the Earth from South Carolina to Toronto. What we're trying to do is find the length on that arc. Well, what I need to know in order to do that is figure out what's the central angle right here. The central angle is if this was 33 to South Carolina and 43 to Toronto, then that must be a total of 10 degrees. Okay, as soon as I know that that angle, that central angle is 10 degrees, the length would be the radius times theta. But oops, don't forget, hopefully you haven't in the last few minutes here, we need that theta in radians. So 10 times pi over 180 is going to turn into, you don't even have to reduce these, by the way, but why not? Pi over 18 seems simple enough. And therefore, the length equals the radius. The radius of the Earth is what we're looking for. Given that the radius of the Earth is approximately 6,400 kilometers, the book might use this as an approximation as well. I'll have to talk about that when we get to class, but 6,400 is a typical approximation for the radius of the Earth. Okay, and then theta we know is pi over 18. So although I can get this exactly in terms of pi, it's probably going to mean more to us if we do round this one. Okay, so let's type this in and see what we get. 6,400 times pi, oops, wrong thing, pi divided by 18. And we get that that is 1,117.0, something like that. Okay, so what I want you to think about in terms of rounding here, oftentimes it will say something like round to the nearest 100, not hundredth. Okay, so not this thing where we go to 2 decimal places out. We might actually round to the nearest hundreds place, right? The ones, the tens, here's the hundreds place. So if I want to round here, I would look at what comes after it and say, all right, well, based on the fact that this is a 1, that's going to stay a 1, so therefore it's approximately 1,100 kilometers. And the reason why we're rounding to the hundreds place in questions like this is if I say, oh, it's actually 1,117 kilometers, that's not a big difference in the grand scheme of how far apart those two cities are. If we say, yeah, it's approximately 1,100 kilometers, that we get the point across. So please read rounding directions as it relates to this. Oftentimes, it will say round to the nearest 100, not hundredth, 0.01. You know, if we're off by 0.01 of a kilometer, we're probably still fine. Okay. All right, we'll save this one, like I said, for class tomorrow. Let's move on and talk about another, this is a third formula today, and you can see the derivation for the area of a triangle here. So when calculating the area of a triangle, we're going to base it off of what we know from 4th grade math. 4th grade math tells us that 1/2 base times height is a formula for the area of a triangle. Well, if you look at sine of angle A, we're going to use this little triangle over here. Sine of angle A would equal opposite over hypotenuse. That's where h over b comes from. Therefore, what's the height? If you multiply both sides by b, you get height equals b sine A. So that's going to get replaced for b right there, or for h right there. And then what's the base? The base is the length c. It's across from angle c. So if I replace the base with c and the height with b sine A, you simplify to this formula right here, just a rearranging, becomes 1/2 bc sine A. Let's take a look at where that is in the picture. So you can find the area of a triangle by making some substitutions to 1/2 BH if you know these two side lengths. So here's B and here's C. And you know the angle in between those, which is why I've written you need a side angle side setup in order to use that formula. So why is this to our advantage to have this formula? I guess if you don't know the height of the triangle, you might be able to easily measure two sides and the angle in between those sides with some measuring tools in the world. But maybe you don't know the measure of the height. Well, you can find the area of that triangular region by making some trig substitutions and getting to this formula. It's pretty user-friendly, okay? Two sides of a triangle measure 28, 35, and the measure of the angle in between these sides is 47 degrees. This angle, by the way, can be left in degrees. Don't worry about it, okay? Whereas the other two formulas, I made a big deal about needing radians. We don't need radians here. So the area would be 1/2 of 28 times 35, and then at the end, sine 47. It was important, by the way, that it said the included angle between these sides. If we don't have that included angle, if we don't have a side angle side setup, then we have to do a little bit of work to get there, okay? I'm gonna double check that I'm in degree mode, which I'm not, okay? You do need to be in degree mode in order to type in sine of 47 degrees. So if you need to adjust on your calculator, go ahead and do that. 0.5 times 28 times 35, and then sine 47 is approximately 358. I'll go to the nearest square inch. I don't know if it said where to round, but 358, and we're back to area now. So we've got inches squared for that area. Notice how we're only going to do one quick example there. I promise there will be more that involves area of a triangle, just like that. There's another method that we're going to learn, though. And method 2, it says, if we know all 3 sides. I'm going to offer up this method without a proof of why this formula works. There might be a proof in your textbook if you're interested. But the alternate formula is called Heron's formula. Heron was a Greek mathematician who was able to determine that if you know all 3 sides, this formula right here can help you find the area. Now, what are A, B, and C? A, B, and C are the 3 sides. A, B, C. But what is this thing called S? S is represented by the semi-perimeter of triangle ABC. Semi-perimeter is exactly what it sounds like. It's half the perimeter. So if you can calculate that, then we can use Heron's formula pretty easily here. So given 3 sides of a triangular lot, okay, a surveyor finds the edges of a triangular lot to measure these 3 lengths. What is the area of the lot? Well, can as easily use this formula up here because I don't know the included angle for any of those sides. So let's find S, which is that semi-perimeter. You're going to take 42.5 plus 37 plus 28.5 and divide that by 2. It's not an average of the 3. It's a half perimeter. So take that perimeter, cut it in half. I'm going to do a fancy fraction just so I don't mess this up here. 42.5 plus 37 plus 28.5, and then divide that by 2. Oops, nope, not by 5. Hang on. Let's try that again. Okay, is 54. So once you have the semi-perimeter, now we're just going to plug it into this formula. So therefore, the area equals big radical. First thing we're going to write is S, which is 54, times 54 minus, it doesn't really matter which one you call A, B, and C. Doesn't matter. But A is 42.5, so 54 minus 42.5, and then 54 minus 37. Finally, last one, 54 minus 28.5, okay? This is another way to calculate area of a triangle given all 3 side lengths. So let's see if I can type this in carefully. Square root of 54 first, parentheses. You don't even have to subtract those unless you want to, but let the calculator do the work. 54 minus 42.5, 54 minus 37 is next. At the end, 54 minus 28.5 to get an area of approximately 500, and it would round to 519. Okay, 519 square, and this is meters for this one. So I've thrown 4 different formulas at you so far today. We have area of a sector, sector of a circle, arc length of a section of the circle, area of a triangle, okay? And that sort of rounds out the amount of formulas you'll have to know. This is a formula heavy day, but you know that combined with law of sines and cosines, those are the formulas you'll have to know for the next quiz. All right, on the last page here, we have some other area practice. And I think what I'll do is let me just do the first example with you, finding the area of a segment. Once I'm done with the area of a segment, we'll do these 2 next time we're in class together. So to find the area of a segment is exactly what's shaded below here. The segment is cut off by a chord of the circle and this arc, okay? So to find the area of that section, we're going to subtract 2 areas that we know how to find. It's going to wind up being the area of the entire sector. Remember, sector is the piece of the pie. If I take the area of that whole sector of a circle and subtract the area of this triangle that's not shaded at all, that's going to leave me with that shaded region right there. Well, as a reminder, 1/2 r squared theta is going to wind up being the area of the sector. The area of a triangle, we have side, angle, and we know this side as well. If you have side, angle, side, you can use 1/2 AB sine C, the formula we just learned a minute ago. Okay, so let's plug in what we know and see if we can evaluate here. So it's going to be 1/2 the radius, which is 6 squared. Now, theta has to be in radians. Luckily, it is. That's pi over 6, so that's easy. minus 1/2 of a and b are both sides, the 6 and a 6, and then times sine of pi over 6. I'm going to leave this as an exact answer in the end, but let's go ahead and simplify here. Okay, I know this is 36. 6 goes into 36 6 times, and then half of 6 is 3. So this whole thing becomes 3 pi if I leave the pi out of it, right? And then over here, let's see what we have. Sine of pi over 6, by the way, that's a nice reference angle. Pi over 6 is 30, and sine of pi over 6 is 1/2. Okay, so that's kind of nice that if I know that, let's see, what do we got? This is 36, and then half of 36 is 18, and half of that is 9. So when all said and done, multiplying all of this together gets you a 9. It's that many square units that represent the area of this shaded region. I went through that kind of quickly, but I'll do another practice like this at some point to make sure we're good with this concept, okay? This is the exact area. If it said round to the nearest, square unit, nearest tenth, nearest hundredth, of course, we could do that as well. All right, so that's it for our lesson today. The examples that we left blank, we'll finish up next time we're together. Have a great rest of your day.